So now we can officially start. Hi guys. So the quiz will be there this afternoon. It'll open up, and it's multiple choice. And the quiz is based on last week's and this week's. All right. Whoa, everything just went wacky on here. All right. So if you guys can't hear me or can't see me or anything, I'm going to share my screen in a bit. But the quiz is based on last week's and this week's. So after we do this lecture here, toot around, try some of the review questions. You know, if there's anything there that's bothering you, get a hold of me and try the quiz. Well, it's going to be paper-based. So you should be able, I'm hoping you should be able to print it off and work on it there on your own. And then when you are ready to submit it, you'll go on to Blackboard to the link, the Akindi link, I think. I hope it's all set up. And you'll just fill in the 20 bubbles, okay? And you'll submit it. That's it. So you don't have to, I think it'll close next Thursday at 1 o'clock. So you have all week to tutor around, talk to each other. That's the new education. Y'all are out there, y'all think you're alone. Well, you're not. You have each other, you have me. And talk to each other. Communicate. Learn from each other. Maybe one week you're a teacher. Maybe the next week your friend's a teacher. Everyone has their strengths and their weaknesses. Play off each other and learn from each other. And just as long as the quiz is uploaded there by next Thursday, 1 o'clock, I don't care. All right? So if there are any questions, shoot me questions. I'm going to try. I'm getting better at this. Maybe I'm not. All right, so here, let's try this out here. I'm going to share my screen. So you should be looking at my desktop. All right, so what I want to look at now is a student there. Great, I love it. They tried a question there twice from last week's review. And then they emailed me just as I asked them to. They said they couldn't get the answer. Can you shoot me the answer? And I saw there. I went and checked it out, and there was an error. I fixed it all up. And I'll show you guys. And I'm pretty sure, I don't know if it was 12:30 or 2:30 in the morning there last night. It's just the way it is for us during these times. And where is that picture? Did I not post it? I'm sure I did. Week 1 answer to syllabus. Week 1. Limiting reagent. 5 and 6. So I did post it. So this is it right here. And some of these, like I obviously wrote all of this because I'm going to go over it right now. Tell me if you guys can't see anything or if there's any issues. I've got my little box minimized so I can't see any kind of, well, I guess I can. But if there's any questions, just give a shout out, turn your microphone on, and away we go. I'm going to try. Is it going to let me? No, okay. Okay, so hopefully now we can kind of see what's going on here. And if you look at the question was, I think it was determine the limiting reagent here. And this is a question here that a student asked there because they wanted to unmute my system's volume. What's going on here? Okay. All right, good. This is one of the questions here, and I just want to go through it. And obviously I wrote all this here because I want you guys to kind of see the step-by-step, but you guys wouldn't be writing this. These limiting reactants, sometimes you can just see them without any calculation. Sometimes you got to do a little bit of calculations to actually see it. And you'll see here by this question, here we have 3 moles of sodium nitrate and 1 mole of sodium phosphate. Oh, and by the way, if there is no number in front of this, there is still a 1. There is. All right. So they got 1 mole of sodium phosphate, 1 mole of silver phosphate, and 3 moles of sodium nitrate. So molar ratio is 3:1:3. Okay. And this question here, I gave you grams and grams. So as soon as you see grams in there, or if I'm asking for grams, be prepared to do at least an extra step. Okay? If I give you grams, ask for, you know what I mean? And so here we need to find out which is the limiting reactant. This is your molar ratio. It's all in moles. All this stuff, when you do your boxes and your crisscrosses and all that, it's got to be moles. All right? But to make your life more difficult, which I don't mean to do, but they make me do it in order to get a paycheck. I got to make your life critically think anyways. This is all about analyzing, critical thinking. And here I gave you 200 grams of this and 200 grams of this. And I'm asking how many grams of this am I going to make. So I give you grams and I'm asking for grams. This is where you go, man, it's going to be some extra work. So, very first thing you got to do, and I hope you guys, I'm pretty sure you guys are programmed for this. If I give you grams, the first thing you got to do, change it to moles. All right? So, what I've done here is I've, quick like a bunny, I've changed these there to moles. Okay, you use the formula, number of moles is equal to grams divided by molar mass. Y'all always have your molar masses. You can calculate those out. So anyway, what we're looking at here is I got 1.17 moles of this, 1.22 moles of this. I'm going to try and figure out how many moles of this, and then my very last step, I'm going to convert this into grams, and that's going to be my answer. Now, you could go through the whole mathematical steps here. Like the whole idea with limiting reactant is which one is going to go to zero? Which one is there going to be excess? All right. So here I've got basically 1 mole of this and 1 mole of this. But let's go back to our molar ratio. In order for these 3 moles to go to 0, I need 1 of these guys to go to 0. So it's 3 to 1. Well, you look at this, I basically have 1 to 1. So you can kind of see 1 of these guys reacts with 3 of these guys. Well, you can kind of see, hopefully you can see where you're going here, that and how I do this, I break it down. You don't have to do it this way. Some people can just figure it out, you know, go for it. But what I do is I create scenario 1 and scenario 2. So what this means is, if this is going to go to 0, if 1.17 moles is going to go to 0, we do a box. 3, 1, 1.7, and I find here 0.39 moles. So in order for this to go to 0, I need this amount. So this is hypothetical. This is real. This is real. I've given you those two. So in order for this one to go to 0, I need this amount of moles. Do I have 0.39 moles of this stuff here? Well, I do. I have 1.22 moles. So since the molar ratio is 3 to 1 for scenario 1, if 1.17 moles are used up completely, then only 0.0 or 0.39 moles of sodium phosphate is used up. X. Okay? Which we do have, and this is excess, so this statement could be correct. It is correct. Because if one statement looks correct, the other statement guaranteed will look false. So these are my real values right there. We just worked it out for scenario 1. So this is my real value for scenario 2. I do another box. 3, 1, 1.22, and Y. Do another box. And you find out here that in order for 1.22 moles to go to 0, I need 3 times its amount to go to 0 over here, right? 1 to 3. So I do a box and I find out that since the molar ratio is 3 to 1, if 1.22 moles of sodium phosphate are used up, then we must have used 3.66 moles of silver nitrate, which we don't have. So in order for this guy to go to 0, I need this amount of moles for this guy over here. But remember that this X and Y are hypothetical. This is all I have. So I do not have 3666666 moles here. So scenario 2 is false. Cancel it. This is what is going to happen. Okay? And I've kind of rewritten it out here. You won't have to. When you guys see my quiz and my tests and my assignments, you won't have to do all this finagling around. All right? You'll see there that I'll show you a copy of the quiz there, and because it's going to be open anyway, and I'll show you that. So what I've done here is I've rewritten it. Okay, and we're going to go with scenario 1. So 200 grams, X grams, same thing as above. 1.17 moles. Okay, so I do my box. Sorry, you guys can't see. And I find out there that 0.39 moles, which is what we had up here. Okay, so that's what's going to happen. So this is 0.39 moles in here. So that's what we're going to be using up. So that's all of this that we're going to use. What's my molar ratio? 3:1:1:3. So this is a 1. This is a 1. So these guys are going to be the same. So if this is 0.39 moles that are going to be used up, well, I'm only going to make 0.39 moles of this. Ratio 1 to 1. Same banana. So we go down here. So 0.39 moles of silver phosphate. Okay. Find the grams. Use your formula. Grams is equal to moles times molar mass. 0.39 moles times 418.58 grams per mole. Okay. Quick Google search. But be careful. If you just type in molar mass of silver phosphate, make sure that your formulas are correct, because it may give you a different molar mass. Or you could just add it up yourself. And you get 163 grams of silver phosphate. Okay? That's how we do it. And right over here, silver nitrate is a limiting reaction, and we'll go to 0 using 0.39 moles of sodium phosphate there. And this is the answer there to number 6. We only use 0.39 mole. We started with 1.2 moles of silver phosphate. This question here is asking for how much excess sodium phosphate is left over from here. Well, we only use 0.39 moles of it. So 1.22 minus 0.39 gives us 0.83 moles excess. And then your moles, your molar mass, and you calculate the grammage. That's how that one goes. All right, because you will see this on the quiz. Hopefully there, you're not writing all this. You shouldn't have to write all this. I'm writing all this, and I apologize. It is what it is. But hopefully there you guys can follow it, and you guys have any issues with that, you guys know, just give me a shout and we'll get through it. Okay? So that's there. That's a good limiting reagent. Honestly, that's about as tough as you're going to get. Sorry about that. Yeah, that's about as tough as you're going to get. I give you grams for both of them, and I'm asking for grams at the end. Yeah. All right, so first thing you do is gets it into moles, do your boxes, and sometimes you don't need to do the boxes. Sometimes you can just visualize. Maybe you'll see that on the quiz. We're going back here. Now, if there's anything there that else you guys need, you guys just keep asking me. That's what we're looking for here. And I think I've got something else hidden over here. Where is that? These are this is the formula sheet there for this week and last week. And it will be accumulative. All right? Or cumulative. All right? And so like next week there, you'll have week 1, week 2, and week 3. And so here are the formulas there from last week. These are the formulas here from this week. Okay? They're new, but again, you don't have to memorize them. They're here. And all these formulas, these triangle formulas, are plug and play. All right? Don't kind of freak out here. These guys here are the same as this one. I think there's one in here that's not superimposed as a triangle, and it's parts per million. Okay? But all of these guys here, I've transformed into triangles. You guys remember your triangle? Throw a thumb over what you're looking for, and then that tells you what you need. So, also a little thing here that I just did there that's new there this year, I added this, was these circles. I put a circle around everywhere where you see moles. So in this formula, moles is equal to grams divided by molar mass. This one here is moles is equal to the number of atoms or molecules divided by Avogadro's number. We've got molarity, which is a new one there today. It's not bad. You'll be fine. Molarity is equal to moles per liters. And here I've got something called molality. Again, it's not bad. Which is moles per kg of solvent, which we'll get into there today. All right. And the reason why I did this is because now you have a bridge between all of these formulas. Okay? And, you know, I may give you this information over here and ask you to find this information over here. Well, how do I get from here to over here? Well, I give you this information. You find the moles, submoles over here, and then you find out what you can. But we'll get there. We'll get there. I just wanted to show you what these circles mean, that there is now a link between all these formulas with moles. Other than that, I hope the labs are going well. I don't think they're that bad. And I'm not a bad...
Can I ask you a favor about lab 1 and to do it as a Word document?
Sure. Yeah, ask me. Go ahead, quick.
No, I want, like, if you can post the lab 1 as a Word document.
I can. I guess I can, but the issue with that is people will upload it as a Word document, and the last semester was a bit of a nightmare. Like this class is kind of a small. I think we have 39 or 40 students, so it's that's, as far as class sizes go, it's not bad. But I had a class of 70 students. You know, every week we were in the lab, and they were uploading labs every single week. And the biggest problem was people uploading labs or Word documents that were encrypted. So you needed a password or some type of pass key to open it. And when it's 2 o'clock in the morning and I'm marking these labs, and out of 70 labs, 17 of them I can't open. So then I got to email 17 students. And whenever they read the email, they send it back to my email, because you can't post another assignment into the same spot that you already posted an assignment in, right? So now I've got 17 emails for lab 4 that are sitting in my 17 labs sitting in my emails for lab 4, and this is going on lab 5, lab 6, lab 7, lab 8, and it was a bit of a nightmare. So I'm a little afraid of Microsoft Word. If I'd rather keep it as a PDF, but I can post it as a Word document, but please only upload PDFs, okay? Because that just guarantees there that it'll open on Blackboard, and I'll have a smile on my face, because you would like me to have a smile on my face while I'm marking your paper, wouldn't you? Okay, if there's any issues, let me know, but yeah, I can post that. Good question. Thank you.
Ian, I have a question as well.
Yes, who am I speaking to? Sorry. And I didn't ask. Who was I? I'll ask who I was speaking to there before, but I didn't. Who am I speaking to?
This is Alexander. I think you were speaking to, I don't know how to pronounce her name, but it's...
Alaya.
Oh, Alaya, that's right, too. I missed it. You went off my screen. Hi, Alaya. All right, go ahead. Go ahead, Alexander. What do you got?
So I think a few of us were wondering if maybe you could, like, scan the notes that you go over in class and, like, post it on for us, because it's a little bit difficult for some of us to follow when we don't have something to, like, physically, like, hold while we're going through, or to, like, look at, like, as you're speaking, or, like, maybe, like, type up some things for us to follow, or post it after class, just so we have something to, like, physically reference back to, like, when we're doing the work.
Well, you guys have, I give you guys all the answers there. They're coming. They're posted with the questions. And like, if you're looking for a specific question, I could do that. Absolutely. So if you need anything posted, let me know. Obviously I can't go through every question and do it by hand or something like this, but if there's any specific questions, absolutely, it's all good. Okay, and kudos. You guys noticed there that there was an error in week 1. I think it was mass. That's been fixed, and I appreciate it. Please do not spend a lot of time on a question that you're not getting the answer to. Do it once or do it twice, and then email me. And it worked out just well. I appreciate that. What other questions we got? Are we good? Okay, let us begin. Solutions. Probably the most important lecture of this first half. Okay, because solutions, basically, this is how we do chem. Look at your body. We're just great big salt water bags. Sorry if I'm sure we all are more, but biochemically that's all we are. And we are just one bag of solution. And this is how the body works. This is how all terrestrial animals, plants on Earth work. This is like the whole idea of organic chemistry. I guess I was in school in Czech Republic, and this is basically, it was Charles University in Prague. Awesome Prague, by the way. What was I saying here? That at the school there, it was it's 700 years old, and originally they would teach chemistry in Latin and all that kind of stuff, but now it's in English. But it was the birthplace of organic chemistry. And what did that mean was that before, some guy, what's his name, Voller, he synthesized urea, P. And before that happened, people thought that fluids, things that happened in the body, they had, I don't know, a heaven-like quality, a God-like quality, and it could not be reproduced. It couldn't be synthesized. There's a spiritual quality that, can't be reproduced here to create living things or living solutions that are inside of us. Well, this guy here made urea. Very simple compound, and completely disproved everything. That now, whoever we thought we are no different than trees and wolves, and we're just part of the ecosystem. And everything that's inside of us, most things can be reproduced or synthesized artificially. And from that point on, brought in organic chemistry. Fascinating. And this all comes down to solutions. And let's go through it here. I added this here. If you guys are having a bit of trouble, have a look at it. Basically, just keep at this stuff. Do not let this stuff slide, because when we get into about week 4, it'll get a little heavy. Okay, this stuff here last week was review. Today's stuff is not bad. There's 6 triangle formulas that you don't have to memorize. You just have to know how to use, right? So, but about week 4, it'll get a little heavy. Do not let it slide. If you're having issues, please contact me. We'll set up a WebEx. We'll get her done. We'll get you guys through. And if you absolutely hate this stuff, it's all good. The second half of the course is where you want to be anyway. So just get through this. If you're having trouble, let me know. Just be preemptive on this, okay? If there's no other questions, we'll move forward with this. It's not a bad PowerPoint. I'm hoping there about an hour 10. And then there should be some room afterwards there for some questions. My wife just had minor surgery, so she's out. And my kids are downstairs, so there might be interruptions. You might hear a stampede of buffaloes. You might hear crying. You might hear, somebody getting whacked on the head. So not by me, but yeah, 7 and 4 years old. What are you gonna do? Kinetic energy. You'll need this there for your physics as well. Just because something looks like it's not moving, like the desk that I'm sitting at, or this coffee cup, it's not really moving. Everything is moving as long as it has heat. And if you look at water can be a solid, all right? And you look at the molecules there when it's a solid. They're not moving. Ice is not free. The molecules in water are not free. They're vibrating, okay? Anything that has heat will have a bit of motion to it. And then if you keep adding heat to the ice, what happens is it's kind of like a popcorn effect. All those molecules that are locked in at the ice, okay, like the picture, if you add heat to it, what happens is these molecules are now free. But they're not so free that they can just fly off and go to Bermuda for a week. They're free enough that they can move around, but there's still enough of a connection there between the molecules that they move freely, but they're still kind of tied to each other, and that's water. And we're going to get into water in a bit. Water is the most amazing substance known in the universe. It shouldn't exist as a liquid. But because it's bent like this, you guys there remember from, what was that, week 3 lab there last year? It's a bent molecule. That's the whole thing. Like if you take a piece of string and put it up to the top of the mouth of the tap and hold your string over here like this, right? So it's kind of down. And you turn the water on a little bit. That water will snake along the string. It will not go down. It snakes along because water has this property there. Because it's bent, it's a very polar molecule. You remember that word there from last semester, eh? Polar. Good, because we're going to hit there. And water is a crazy molecule. It's only 18 grams per mole. You have an oxygen, which is 16, and 2 hydrogens, which is 1 and 1. So that's so it's 18 there. But water, you can drink it, you can swim in it, you can have a bath in it. But then if you do a backflip off a diving board and land on your back, then all of a sudden water can turn into cement, right? So we'll get more into water, but you'll see there that water has more of movement because it has more energy. It's a little bit more free. If you keep adding energy into that water, you will get another popcorn effect at 100 degrees Celsius. Choom, choom, choom. Now this water is more free, and that's what we call steam, right? And you can even keep adding energy, and you will actually get a fourth state of matter called plasma. We'll get there in the physics. But kinetic energy has to do with heat. And as long as anything is above 273, minus 273 degrees Celsius, absolute zero, it has heat, it'll have motion of some kind, whether it's free moving like this, or kind of free moving like water, or if it's just vibrating like a solid. Water is strange. And when you guys get into, I don't know if you guys hit it there last, I think you would have there when you did DNA. DNA is a massive molecule. Like it's just enormous as far as molecules go. And what keeps this double helix all together is the same reason why water, if you do a backflip off a diving board and land on your back, you could potentially paralyze yourself and break your back, because water has this quality to it that it can kick back at you and be like cement. And it's all because of hydrogen bonding. And if you have a look at frozen water, aka ice, you'll see there that it forms these hollow rings. And that's how ice looks. And it's very porous in a sense, meaning that it's less dense than liquid water. This is what liquid water looks like. And it's denser. There's, and what does dense mean? In 1 cubic centimeter of water, liquid water, you have more atoms than 1 cubic centimeter of ice. Let me repeat that. In a cubic centimeter of water, you have more atoms or more molecules of water than you do in 1 cubic centimeter of ice, because ice is like this, right? So therefore now ice is less dense than liquid water, which is why the ice floats in your Diet Coke. It's the same reason why a 1,000,000-ton iceberg will float in the ocean. So this is what we're dealing with here. And what is hydrogen bonding? Have a look at that. And it all has to do with, there's got to be a hydrogen on one end, and hydrogen is generally +1. You remember oxidation numbers? Oh yeah. Oxygen is -2. Let me tell you a little bit about oxygen. When you have a lasagna and, a really good lasagna, there's nothing better than a really good lasagna. And then you've eaten, and then there's all the crusty bits that's left in the lasagna pan. Well, there's no way in heck I'm not going to spend 2 hours scrubbing this thing. So you're either going to throw the pan out, or you put some water in the lasagna pan and you soak it overnight. And what happens there tomorrow morning? You just take a rag and just give it a quick wipe, and she's good to go. What happened between last night and now? Why just putting water into a lasagna pan and the water attacks, and so it's easy to clean off all the dried, burnt little bits of lasagna? It has to do with oxygen. Oxygen is what keeps us alive, right? Like last week there, I told you guys there that when we eat a banana, we're actually burning it. Because we breathe in oxygen, you need oxygen, okay, to burn anything, all right? And that's what oxygen is. We need oxygen there for living, for energy. But oxygen is also a very aggressive atom, all right? And it's the oxygen in a water molecule, right? You guys know you're too high. Sorry, I'm trying to find the camera here. What's going on here? Let's move that. Is that all right? There we go. So oxygen looks like this. The water molecule looks like this. It's a bent molecule with your oxygen up here and your 2 hydrogens down here. Well, your 2 hydrogens down here, oxygen here. Who's the big banana? Who's the big boss of the molecule? It's the oxygen. It's very electronegative. Very. It's so electronegative, in fact, that it scoops up electrons. It attacks other atoms. It's a bully, basically. Oxygen is a bully. And there's only one other atom that's even more electronegative, and that's fluorine. So oxygen is very electronegative. It likes to hold on to electrons. It's very aggressive. So that's why when you put water into a lasagna pan, what is attacking the dried bits of lasagna? It's the oxygen. So oxygen is good for us because it allows us to live. Gives us oxygen so that we can break down our food, burn it, extract it, lift weights, go to the gym, do whatever we need to do. But oxygen also has a downside. It's the atom there that causes wrinkles and eventually takes us out. So it's a double side. It's good and it's bad. All right. So please have a look at hydrogen bonding. Oh, hi. There we go. There's trouble. Oh, hi, Shire. Oh, and there. Thank you. I needed that. Now, can you take Harley out? All right. Bye-bye. That's it. Harley, out you go. Sorry, guys. Come on. Hey, let's go. Come on. Let's go.
But I'm showered.
All right. I'll get him. Come on. Hurry up.
I'm
Told you this would happen.
I'm showered.
You go and see Mommy.
But I'm showered to home.
Okay. Hold on. I gotta... All right. I knew this was going to happen. But anyway, we're good. Funny times. So what we've got here now is oxygen, is electronegative. This is the whole thing. It's a very aggressive atom. And when you have an electronegative atom and a hydrogen, what will happen is they'll kind of form a little bond. Now, think about it. Liquid water is moving all around like this. But because, remember I told you, it'll go along the string when you turn on the tap. It'll snake along the string because of this hydrogen bonding. Okay? It will, each molecule is kind of, for a fraction of a second, attracted to this one, and then it moves over here and it's attracted. So there's a constant attraction going on in between all of these molecules, which is what makes water a liquid. Because anyone here who smokes, or you have a lighter or something like that, you look at what's in your lighter and it's butane. That's in your lighter. And if you just hold it without lighting a spark, okay, that butane, which is a liquid in here because it's under pressure, if you release it, it turns into a gas. And butane is what? 48, what is it, 6 to 70 grams per mole? It's kind of a bigger atom. Sorry, 60 grams per mole. Water's only 18. Butane is not a liquid at room temperature. Water is a liquid at room temperature. It's such a small molecule, it shouldn't be a liquid. But it is because of this hydrogen bonding. Okay? And have a look at it, read it. There's 100 million vids on this whole process there on YouTube, so have a look. Okay? I just want to go over this classification of matter. All matter in the universe can be broken down into mixtures and pure substances. Okay? Pure substances can be broken down into 2 bananas here. We have elements, periodic table. Oxygen, gold, iron, beryllium, nitrogen, you name it. These are all elements in their pure form. Okay? But then there are compounds. Salt, sodium chloride, okay? Baking soda, sodium bicarbonate, sugar. You can have a bowl of pure sugar. That's a pure substance. It's one banana, one thing, all right? But today, we're going to be focusing on mixtures. And there are 2 kinds of mixtures. There's heterogeneous and homogeneous. All right? Oh, God. My son Shire left the cat and the dog here. Oh, boy. Come on there. Come on there, Leah. There you go. Come on there. Hold on here. Come on, you guys. Out you go. See ya. Come on. See ya. Okay. Hold on. Go, George, run, run! It wasn't as bad as I expected. But I anticipate it's probably going to get worse. Mixtures. Heterogeneous mixture. I use the example pizza. The reason why, you have a piece of pizza, and let's say you get, you have pepperoni, green pepper, onion, cheese, you know, you got the crust there. If I take a little bit of the pizza here from this side of it, and then a little piece from this side, and then a little piece from this side, and I look at those pieces under a microscope, are they all going to be the same? No, this one's got this piece has got pepperoni on it. Well, this piece here has green. So they're not chemically identical. And dirt is another example. If you take a little bit of dirt from here and then a little bit of dirt from your neighbor's backyard, you look at them, analyze them scientifically, chemically. Okay, it's dirt, but they're not identical. Okay? Blood. You know what I mean? Blood is a concoction of all these different things. So a little bit of blood here isn't... We like to think of it as all identical. But there might be a little bit more, there just might be a little bit more somewhere else, or it's not completely identical. And for sure thing, milk. All right? So a heterogeneous mixture, use the analogy of a pizza. It's not identical. You've got a mixture of a whole bunch of different things, and, that's how that one goes. The one there that we're going to focus on there today is something called a homogeneous mixture. And if you look at lemonade, gasoline, if you take the gasoline out of, and put it into a jerry can, and then you take it back and scientifically analyze it, you take 5 milliliters, and then you take another 5 milliliters of it, and then you take another 5 milliliters of it. And if you look at the 5 milliliters of each one, they're identical. There's no difference. If I take sugar and water or salt and water, mix it in there, stir it around, okay, the salt is gone or the sugar is gone. It just kind of looks like water, right? And if I take a little bit of each, a milliliter here, they're identical. And this is what we call a homogeneous mixture. It also has another name that you'll know. It's a solution, where everything, all the atoms are completely spaced out. Everything looks identical throughout the entire solution. That's why we call it a homogeneous mixture. A heterogeneous mixture, pizza, it's different all over the place. But a homogeneous mixture is 100% identical. And this is where we're at there today. There are 2 parts to a solution. Okay, a solution is a homogeneous mixture of one or more solutes and solvents. Solutes and solvents. So what is a solute? The solute is what goes in. The salt, the sugar, these kinds of things. The solvent is what takes those. So it's like the liquid, the water in the cup. And I'm going to show you that that isn't necessarily the case. But, so the water is the solvent. The sugar that you stir into it is the solute. Okay? How are we doing? Is there any, you guys okay? I don't have my little dialogue box up, so if there's any issues, just turn your microphone on and give me a hey, hey, hey. Did you know what coffee? What differentiates a solute from a solvent? Simple answer. Whichever one you have more of. And I'm going to show you that. And you think, if I have 5 grams of sugar and, 100 grams of water. 100 grams is 100 milliliters of water, right? Which one do I have more of? Well, you got 100 grams of water, so that's my solvent. Okay? Whatever I have less is my solute. So, the only solutions that we're accustomed to generally in society is liquid solutions, like Gatorade. By the way, don't ever waste your money on Gatorade. I'll tell you about that in a second. Complete waste of money. Solutions we think of as, what? A solid crystal dissolved into water, right? Like Kool-Aid or sugar or whatever, okay? But it's not necessarily true. Question 2, is air a solution? And if so, what is its solvent? And I guess with pollution, even you go to Toronto, I've been all over Southeast Asia and all that, and London wasn't good either. But the air quality, I guess before people came to be, let's call it like that, right? Before pollution came, the air all around Earth was the same. And what do I mean the same? Nitrogen, 78%, oxygen, 21%, argon, 0.93%, and carbon dioxide, 0.04%. These are pretty consistent around the planet because your air is my air, you know, and with greenhouse global warming, this is increasing. But if you look here, air is composed of 78%, 21%. So you look at this, and by my definition, is this a solution? Is air a solution? Can I take a little bit of air here in Barrie and a little bit of air from South Korea, a little bit of air from Uganda, and a little bit of air from Brazil? You would find out it's the same all over the planet. So air is a solution. Weird, eh? Which is the solvent? Which are the solutes? Well, whichever one you have the most of, right? So nitrogen is the solvent. Oxygen, argon, carbon dioxide are all the solutes. What do you mean I can have more than one solute in a solution? Well, you have your glass of water, you put in 5 grams of sugar, stir it. Can you put in 5 grams of salt? Sure. So now you have salty, sugary yuckiness. All right? So you can have more than one solute. Can metal be a solution? Your ring, all right? The necklace around you. These things are never what we call 24 karat gold because that's 100% gold, all right? 100% gold is very malleable. You can bend it, twist it, take your fingernail. You can actually even kind of cut it with your nail, okay? So we don't use 100% gold in any type of jewelry. We always put a little bit of another metal in, with the copper, okay, these kinds of things. That because the gold is, and silver as well, very malleable. If you mix in a little bit of copper or tin or one of these things, what happens is it becomes harder. So therefore now you can wear it around your neck and hold it, and this thing is not going to break. Okay, so what they do is they melt the gold down, throw in a little bit of tin, stir it around like a witch's brew, and then they put it into a mold, and therefore now your chain or your ring or whatever it is ready to go. But if I chemically analyze that ring that is 90% gold and 10% tin, you will see that if I take a little bit here, a little bit off the ring here, a little bit off the ring there, look at it under a microscope, they be exactly the same. So, metal alloys, A-L-L-O-Y-S, alloys are solutions. Chemically, they're solutions. So, solutions can be liquid, solutions can be gaseous, solutions can be solids. Okay? These are all homogeneous mixtures. When you're making a solution, this gets back to oxygen and its aggressive nature. All right? So there's the whole lasagna pan thing. What happens when you put that water in the lasagna pan and you go nappy nap? Water molecules, they instantaneously go to the lasagna and they'll cluster around it. Okay? The same thing if you're putting sugar into water. That sugar goes in, the oxygen is going right towards it, man. All right? To cluster around it. What is this? And then what happens is the water molecules start breaking this guy up. The oxygen starts attacking it, right? And starts breaking the lasagna, that, you know, a big hunk of lasagna sitting on the edge of the pan. Well, what happens there, slowly over the course of a night, the water is pulling off pieces of it. And then there by morning, there's just a little bit left that you can just wipe clean. The rest of it is gone into solution. Okay? And then the last part there, the solute spreads out evenly, which is the whole definition of homogeneous mixture. Not saying there that your lasagna pan full of water is a homogeneous mixture. I'm just saying there that was there to tell you there how aggressive oxygen is. But when you put the salt into the water, what happens is the water surrounds the salt, breaks it up into even smaller pieces, and spreads it all out throughout the entire glass, so that eventually the glass is completely, the salt is all throughout everywhere, the water is all dispersed, everything is even throughout the glass. Okay, 3 things there: cluster, pull, and spreads out. Okay. Common solutions. I just talked about 3, but yeah, there's actually 6 of them. You can have gas solution, air. Aha, gas liquid, Coca-Cola. And we'll talk about that. You can have a liquid, like antifreeze. For $3.99 Canadian Tire, you buy your antifreeze there, and it's methanol and water, basically, with some food coloring. And methanol, liquid, water, liquid, makes a solution. Liquid, we've got solid liquid. Salt water, sugar water, Kool-Aid, Gatorade. This is where I'm going to do my rant on Gatorade. As I've been gone for 20 years traveling and all that kind of stuff, and I come back there, and my brother and I, we went to the store, and he got a bottle of Gatorade, and I think it was like $4.50, or $3.99 in tax. That was just outrageous. And don't ever buy Gatorade. It's a big scam. If you love Gatorade, if you love that whole thing, it advertises their electrolytes. You need those electrolytes there for your body. So drink Gatorade there, quench your thirst, and get your electrolytes back. Well, all they do is it's just water with salt with a little bit of Kool-Aid put into it. And you notice there that it's not as sweet as Kool-Aid or a sugary drink would be, because they just don't put a lot of sugar in it. Okay, if any sugar at all. I think they use sweeteners now, but they put a little bit of salt in there. That's all they do. And the salt, and you guys, I think you guys are doing muscles there this week. You'll realize how important electrolytes are to muscles firing. Those myofibrils, it's all sodium and potassium. And where do you get sodium? That's an electrolyte. Potassium, bananas, another electrolyte. You need those there across the gradient, because you'll have the potassium ions on the outside, sodium ions on the inside, and when a muscle fires, and then you guys, if you haven't done that, let me know. I can help you with that one. But you need those electrolytes in order for your muscles to fire. Well, where do you get the electrolytes? Salt. So you can make your Gatorade for 10 cents for a big jug like this. Don't ever buy Gatorade again. That's my rant, and I'm sticking to it. You can have another solution, gas solid. Okay, and this one here I'm not really too interested in. You don't have, I would never ask you this on a test, but H2 into platinum and solid. I like this one. Brass. What is that? Zinc and tin? Could be wrong. Somebody Google it and tell me. But all these alloys can be mixtures. What gas is the solute in soft drinks? It's a carbon dioxide. And I'll tell you how. We're going to get into that right there. And what is another solute in soft drinks? So sugarings and flavorings. So if you look at that can of Coca-Cola, the water is the solvent. But dare I say there just might be 100 solutes in there. Sugar, flavoring, coloring, chemical, caffeine, carbon dioxide. So you've got this whole multi-layer of solutes in a glass of Coca-Cola. What do we got here now? Where are we? This one here, very important. Solubility. What we're talking about here is that any amount of solvent, it has a breaking point. It can only hold as much as it can hold. God, that didn't sound right, but I think you get it. You got a glass of water here, and you throw in some sugar. Stir it around, sugar's gonzo. Add some more sugar, stir it around, sugar dissolves. You keep adding sugar, and eventually there's going to be a point where the sugar is just going to go right down to the bottom, and you're going to start to see white crystals on the bottom. That's because the water can't take any more. All right, and there's a couple factors there. The volume of water, sure, the volume of water can only hold so much, but you go back to kinetic energy. Okay, colder water, think about the atoms. They're kind of moving very slowly because it's cold. So yeah, we can take some sugar, we can take some salt, but we can't hold very much. But if you increase the temperature of the water, get it warm and hot, what happens to the molecules of the water? They start moving around like this, and the hotter a temperature gets, the more sugar you can put in. We'll get there, we'll get there. So solubility is just a word that we use to describe the amount of substance that will be dissolved in a specific amount of solvent at a particular temperature. All right, so for example, 36 grams of sodium chloride is the maximum that you can dissolve into 100 grams of water at 20 degrees Celsius. I'll show you this. I have a good little graph there to show you. Miscible. And these little definitions are great for questions. Great for questions on tests and quizzes. Okay. Miscible is the term used if two liquids are dissolve into each other. Okay. So miscible means two liquids that'll go into each other. Immiscible is used if the liquids will not dissolve into each other. Can you think of... Oh, we have one right there. Water and oil. Polar, non-polar. They no like each other. All right? So the water and oil, immiscible. What do we got here? I'm not going to go too heavy into this. It's just that some compounds are very, very soluble. Some compounds are not. And if you look at these guys right here, sodium, potassium, ammonium, nitrates, NO3s, these guys here are if a compound has any one of these, generally they are soluble in water. If you see atoms like this, and you'll see they're pretty heavy, like platinum, mercury, silver, barium, strontium, lead, these are massive, massive atoms. And if a molecule has one of these guys in there, it's generally not soluble. Not a rule of thumb, but just to give you an idea of what goes into water and what won't. Getting back into electrolytes and their importance. We as I said there, we need electrolytes there for muscles to fire. And we need these guys in solution. And if you have, and what we've done here is, you'll see here we've got, let's say a beaker of water with, like this one here. Has a lot of ions in solution. This one here has a lot of ions, and this one here, it does have molecules dissolved in it. But something's different is going on here. If you have a glass of just distilled water, and if I hook up wires there to this, will it conduct electricity? Does pure distilled water conduct electricity? It doesn't, because there are no ions in solution. It's just molecules of water. All right? Well, then you're asking me, why did Mama, when I was 5 years old and I was swimming in Kempenfeld Bay and there was a storm coming, why did Mama get me out of the water? Because the water there in the bay and the ocean and all these kinds of things, it's full of ions. So that water there, if lightning hits that water, it's coming right towards you because of all the ions in solution. What is electricity? Electricity is just electrons. They're negative. And they need positives to move them along. All right? And you'll see here, if I put sugar into water, all the sugar does, the sugar doesn't change. Okay? Like if you put you mix sugar and water together, have I changed them at all? I haven't. Can I get my sugar back? Sure I can. Just evaporate all the water and all the sugar will be left in the bottom. So nothing's changed. That's one of the beauties of a solution. Okay? But you'll see here that there are no ions. There's no positive or negative charges. Sugar is a big ring molecule, okay? And it will not conduct electricity. Here we have hydrofluoric acid, okay? If anybody ever saw Breaking Bad, you'll probably crack a smile here. But great TV show. Not promoting anything in it. The weak electrolytes. And you'll see here that when I put hydrofluoric acid, fluorine is the only other atom that is stronger electronegativity than yeah, you get it, than oxygen. So what happens is this will not break up into ions as well as something else. So you see here we have some molecules, we have some ions, so the light bulb will go on a little bit. All right? If I put sodium chloride into water, what will happen is it'll break up 100%. So I've got ions everywhere. So the more ions you have, the more that bulb will go off. Okay? So if something is a strong electrolyte, this is what you're thinking. You're going to produce a lot of ions. If something is a weak electrolyte, it'll produce some ions. Okay, like vinegar, acetic acid. All right? It will produce some ions, but not a lot. A non-electrolyte, none, light bulb is off. Oil and water don't mix. You'll remember this. Water is polar because it's bent. The oxygen at the top is negative, meaning my hydrogens down here are positive. So this side of the molecule is positive. This side of the molecule is negative. So therefore now you've got this little mini kind of battery that can interact with other batteries. The negative end of one molecule will for a fraction of a second be attracted to the positive end of another. And vice versa. And as it's going through, that's why water has all this strength to it. And it's also the reason why if you boil a pot of water, I think it takes the same amount of energy to boil a pot of water as it does to drive to Toronto and maybe back. Water really holds, it takes a lot of energy to heat water up because of those hydrogen bonds, but it also takes a long time for water to cool down because of those hydrogen bonds. That's why people who live in Southern Ontario, we experience a slightly milder winter than other people. Because the Great Lakes, they warmed up all summer and they're still warm in October, November, and December. So we have a kind of a milder winter. It doesn't look like it there today, but we have a milder winter. And we kind of also, the opposite, we have a milder summer because the Great Lakes got all cold in the wintertime and it takes them longer to heat up. Okay? So you have a look here. The water there is polar. And here we have non-polar. And if you have a look here, we'll get there. Pentane, you'll be all over this there in about 8 weeks. Okay? And you'll see here, three-dimensionally speaking, these hydrogens are rotating around. This is a three-dimensional molecule. That's why if you don't like this half of the course, you'll like the second half. And so they're basically, it's the same everywhere. There's no electronegative difference between this side of the molecule and that side of the molecule. Okay? So that's what makes an oil an oil. But if you look at this guy here, okay, this is ethanoic acid. And you'll see here now, you've got kind of the same thing going on here, this non-polar side, right? But then you've got an oxygen over here. That's the second most electronegative. there's going to be this negative shift. So this molecule here is polar. This side is negative. This side is positive. Will this, Ken, do you think you'll be able to do hydrogen bonding? Yes, you will. Because you've got a negative side here that will, for a fraction of a second, be attracted to the positive end of another molecule. So this guy here will experience hydrogen bonding, but these two will not mix. They don't like each other. Ionic solubility. Many ionic compounds. An ionic compound. Ionic compound. Here we're talking about a metal and a non-metal. Sodium chloride, barium fluoride, these kinds of things. So, many ionic compounds dissolve in water because they form ion to dipole forces. So, ion to dipole. Here we're just talking about how the water interacts with it. Once it's pulled it out into solution, you'll see there that these ions, they're surrounded by these waters. Okay, well, all I want you guys to know is that a cation is attracted to cation is a positive ion that's attracted to negative. An anion is a negative ion that's attracted to positives. So you look right here. Sodium ion, sodium plus, cation. Chlorine negative is an anion. That's what I need you to know from that one. Now, going back into putting sugar into the water. There is a point where the water won't take anymore. And that's what we call saturated. It means full. Okay? And a saturated solution contains as much dissolved solute as a solvent will hold at a given temperature. Saturated solutions are always in equilibrium with undissolved solute. So you're adding sugar, and then eventually there's a point where the solution will not take any more sugar. So the sugar you add falls to the bottom. But there is something going on at the bottom. Some of those undissolved are going into solution. Some of the dissolved are coming out. We'll get in there. I think that's week 4 or 5. Unsaturated solution does not contain enough. You can add more. That's what unsaturated means. That's all it means. Okay? There is something called a supersaturated. Now, as I said there in my physics, I can't play these videos, so I don't know, y'all can come back, or but this video is really, really cool. So you've got an unsaturated solution, which means you can add more sugar. You have a saturated solution that's full, but then there's something called a supersaturated. And how we do this is you take your sugar, you take your water, you're adding sugar to it. Okay, and you'll see there that, okay, I can't add any more sugar. There's sugar at the bottom. It's saturated. Well, you know what? I'm going to heat this sucker up. So now my solution was originally 15 degrees Celsius. Now it's 40 degrees Celsius. I've heated it up, and I look at the bottom, sugar's gone. And I can add more sugar to it. And so my 40 degree, it's kind of warm now. All the sugar's gone. I've added more sugar. I added 5 more tablespoons of sugar when before I couldn't. And then what you do is you just leave the glass on the table. And I mean, don't shout at it. Don't call it names. Don't whack the table. Don't jump around. Let it cool down. And when it cools back down to 15 degrees, you'll see there that it still looks like water. It still looks like a full solution. It looks like a solution. But then if you go whack, sorry if I frightened you, what will happen is all of that extra crystal that shouldn't be in there but is still in there will all come out. Watch the video and see. It's really cool. So that's a supersaturated. It's very unstable. Okay. What do we got here? We'll come back to that one there. This is pretty important stuff. There are 4 ways to increase the rate of dissolving solids into liquids, so sugar into water. Okay? Something called particle size, stirring, concentration, and stirring again. Yeah, I gotta fix that. We'll come back. If I just dump a 5 kilogram block of sugar into my glass of water, is that sugar really gonna go into my water? No, it's not. Like, if I dump a 5 kilogram block of sugar into a swimming pool, I come back in a day, that thing is still going to be sitting there at the bottom of the pool. Because if you look at the surface area, the water, the oxygen is going to come and attack it, but it only has 6 sides to attack it from. And if I calculated here, the slide there, the surface area of this block is 864 centimeters squared. So that's what the surface area there that the oxygen has to attack it and break it down. Remember, cluster, surround, pull it out, spread out. Well, what happens now if I make a cut and I make a cut and I make a cut and I break this block up into 8 pieces? Look at that. I've more than doubled my surface area, because now you see this block here, it has a backside and an underside, as do all the blocks. So now you've increased the surface area, and if you've increased the surface area, the oxygen in the water has more surface to attack. So this one here is going to dissolve faster. And if you look at this one here, if I take that 5 kilogram block and smash it into a million pieces, look at the surface area now. It went from 864 square centimeters up to 10,000. So now, that's why if I take a bag of sugar, that's little grains, toss it into the swimming pool, that thing will be gone in a couple of minutes. All right, so you've increased the surface area of your solute. That will increase the rate of solution or dissolving. Stirring, agitation. Stirring rapidly distributes the dissolved solute throughout the solution. Okay? And all you're doing is you're bringing more water in contact with the solute. So that's stirring, agitation, mixing, these kinds of things. That will increase the rate of dissolving. The concentration of salt or sugar solute into there. If you dump a massive amount in, you see here, what we have here is we're adding more salt, adding more, but eventually there's going to become a time where the solution is full, saturated. I can't add any more. Okay? But if your concentration is high, it will reach that point very much a lot faster. Okay, so concentration is number 3. And number 4, which was improperly labeled there before 3 slides, is temperature. If you increase the temperature, you can add more salt to your water. But this is only for, these 4 slides here are only for a solid into a liquid. Salt into sugar, or sorry, salt into water, sugar into water. Things are different for gases into water. Okay, so there are 4 things there for you to remember. You will see those again for sure. If you've ever had a birthday party or a Christmas party, you had people over there, of course, there before the pandemic, you know what I mean, the good old times. You wake up there the next day and there's a half 2-liter plastic bottle of Coca-Cola that's, you know, it's been sitting out all night. The cap's been on it, you know, and the if you take the cap off right now, psh, and then try having a drink of that, yeah, it's flat, it's warm, ugh, don't want it, throw it out, right? The next time that happens, don't open it and don't throw it out, put it back in the fridge. And you see, when you leave that Coca-Cola bottle out, what happens is, because it starts to get warm, all of the carbon dioxide comes out of the liquid, Coca-Cola there, right? All you need to do, don't take the top off, just put that Coca-Cola back in the fridge for a couple of hours. Because how do you get a gas into a liquid? You lower the temperature. You slow those Coca-Cola molecules down so that the gas can get in there. And what they do at the Coca-Cola plant, you increase the pressure. So if you increase the pressure, you're forcing that gas into the solution. So that when you have your can of Coca-Cola and you go, psh, what are you doing? You're releasing the pressure so the gas can escape. But at the Coca-Cola factory, the pressure is really big, so the carbon dioxide just readily goes in. And plus, colder temperatures, gases will go in. All right, so it's kind of opposite. I really like this next slide here. This is a list of all these different compounds. Here we've got lithium sulfate, sodium chloride, potassium chloride, ammonium chloride, potassium nitrate, all these different ones here. And this graph here is called a solubility graph. And on one side here we have grams of solute per 100 grams of water, 100 milliliters of water. So how many grams of each of these can I put into 100 milliliters of water at a particular temperature? And these work like clockwork. Okay, this is scientific, and this is what's going to happen. So if you look at right here, potassium chlorate, okay, and you'll see here, as I increase the temperature from 20, 30, 40, 50, 60, all the way up to 100 degrees, what does this graph tell you? That I can keep adding more to the solution. And if you look right here, at 50 degrees Celsius, I can add, where is that? That's just below 20. So I can add about 19 grams of potassium chlorate to 100 milliliters of water at 50 degrees. But if you look at the same solution at 70 degrees, I can add 30 grams as opposed to 20. And it works this way for all solids into liquids. So if you heat the solution up, you can add more. Look at them all. Well, actually here, lithium sulfate, it actually, the more you heat it, the less you can add to it. Sodium chloride, salt, really doesn't change if you add more temperature. Okay? You really can't add that much more. Look at these two right here. Sulfur dioxide, hydrogen chloride. These are both gases. And you'll see there that the reason why these guys are a different color and going down as I increase the temperature is because they're gases. The colder it is, the more they'll go up. All right? I think there's a question like this there on the quiz, or it could be on the midterm. But all you're doing is use two fingers, because I'm going to ask you, have a look here, see if I can find one here that's really nice. Ammonium chloride, right here. Can you tell me the solubility of ammonium chloride at 50 degrees Celsius? So I want to know the solubility of ammonium chloride at 50 degrees Celsius. Well, you find ammonium chloride. It's right here. 50 degrees Celsius. Take your one finger, go all the way up. So right here, ammonium chloride at 50 degrees. How much can I add? Go out to this side. I can add 50 grams of ammonium chloride. That's all this works. This graph here, you're kind of extending out. Try these out. They're not too bad. Okay, and if you have any questions, let me know. Concentration of solutions. These two words here, they're kind of, what's the word I'm looking for? Ambiguous. Don't be fooled by them. They're dilute just means not concentrated, not a strong solution. Okay? If I have one solution here that has 1 gram of sugar and another solution over here that has 20 grams of sugar, well, the first one is going to be dilute. The second one is going to be concentrated. Now, what do they mean? Well, they just mean that one has more than the other. Okay? Let's have a look here. Okay. That kind of concludes the intro, okay, of solutions. Now we're into the formulas, okay? And again, there's not a single formula there from this week that is a beast. They're all triangles. They're all good to go, okay? The most important is this one. You will be dealing with these as a nurse, as a paramedic, as a vet tech, all the time. Molarity, which sometimes we say molar. Okay? Solutions are sold, bought on their concentration, and we use the word molarity. What does molarity mean? It means moles of solute divided by liters of solution. Not milliliters, liters. Molarity is equal to moles divided by liters. Okay? And there's your triangle there. Put your thumb over molarity, moles divided by liters. I may ask you for molarity. I may give you liters and moles. Okay? But let's have a look here. A 1 molar solution of potassium chloride is prepared by dissolving 1 mole of potassium chloride in 1 liter of water. That's all it means. So 1 molar solution, 1 mole per liter. 2 mole solution, 2 moles per liter. A 10 molar solution, 10 moles in 1 liter. Very strong. And in some cases there, when you're dealing with acids and bases, very dangerous. I made this up here. It's just I wanted to show you that. Here, let's just read this here and we'll see how this goes. Calculate the molarity of 2 solutions prepared both with 1 mole of potassium chloride, and one solution will have 1 liter of water. The other solution will have half a liter of water. So they both have 1 mole and 1 mole of solute, but this one here is going into a liter of water. This one here is going into 500 milliliters of water. How is that going to affect the concentration? Think about it. 1 mole, 1 mole, 1 liter, half liter. So here we go. Molarity is equal to moles of solute divided by liters of solution. This is for the first. 1 mole divided by 1 liter. So in the first scenario there, 1 molar solution of potassium chloride. Let's try the other one. Still had 1 mole, but it's only half a liter now. So what's 1 divided by 0.5? 2 molar solution. So you'll see here that this solution is double the strength. Everything isn't in 1 liter. Because, we could have 500 milliliters, 200 milliliters, these kinds of things. 10 liters. So the concentration, we can figure it out. Moles divided by liter. And you see in this case here, 1 mole divided by half a liter is a 2 molar solution. Stronger, more concentrated than this guy here. Here's another one here. Everything you've learned in your bag of tricks you have to carry with you, which is why the formula sheet is cumulative. Week 1, you've got to have it to do week 2. Week 1 and 2, you've got to have it to do week 3, and so on and so forth. So have a look here. Look at this molarity question. Calculate the molarity of a solution prepared by dissolving 9.35 grams of potassium chloride in enough water to make 250 milliliter solution. So here I've got 9.3 grams of this going into 250 mils. What's my molarity? Well, molarity is moles per liter. I ain't got moles. I got grams. Well, go back to your formula sheet there. You remember those circles? Use the first formula there with grams. Find out the number of moles. And then you plug that number into your molarity formula. Because grams we can change to moles, and that's what I've done here. So you got knowns, 9.3 grams. Solute must change to moles first. 250 milliliters of solvent, water. Aha, you must change to liters. So 250 ml. So before you can do molarity, you got to change grams to moles, which I've done here. You can check my math. And then now you've figured out that 9.35 grams is equal to 0.125 moles. Plug that back in. Here you go. Be careful, 250 ml is equal to 0.25 liter. You calculate this out and you get there. There's your molarity. Okay? If there's any issues with that, let me know. Okay? You're going to see there that the carpet we're going to be walking on, it's going to seem very familiar. Okay, like you've walked this path before, because you're still going to be using the same formulas there that you were using there before. This is a good one. Okay, dilution. Let's say you've got a 1 molar solution and you want to dilute it, make it weaker. You're going to add water to it. So the same solute is in there. You didn't change you didn't change anything about the solute. There's still 1 mole of solute in there, but you've doubled the volume. So therefore now it's going to be a weaker concentration. How do we calculate these things? I know it as M1V1 is equal to M2V2, which is molarity 1 times volume 1 is equal to your new molarity times your new volume, right? If you've got your solution, there's your molarity 1, there's your volume 1. If I add more water to it now, you've now created kind of a scenario 2, where you have a different molarity and a different volume. Okay, that's how you use this formula. You guys might remember that it's the same formula here. You guys, however you guys know it, I don't care. Some people know it as V1M1 is equal to V2M2. I don't care. Some people know it as C1V1 is equal to C concentration volume. Doesn't matter how you know it, it all works. Have a look at this one here. Calculate the molarity of a sodium hydroxide solution prepared by mixing 100 milliliters of 0.2 molar sodium hydroxide with 150 milliliters of water. Okay, so how am I going to do it? Calculate the molarity. Okay, molarity. I have a couple formulas there for molarity. Okay, so I got a solution with 100 milliliters, and it's 0.2 molar. And then I add 150 milliliters of water. So my second solution is going to be more. And they want to know the molarity. So this is a dilution. Whenever you see the word dilution, ding, 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 this is your formula. Okay? So, knowns, I got 0.2 molar initial, M1, 100 milliliters, V1. And then your new volume for V2 is 100 plus 150. So you've got this one, I gave it to you. We got this one, which is 100 mils. My new volume is 250. We're solving for this. So now everything's multiplied. Hopefully there you guys can flip these guys all around. And we're solving for M2. So M2 is equal to M1V1, these guys here. And then you divide this V2 out of here and it comes on the bottom. Plug your numbers in, play. Next question. So this is your, after you're adding 150 mils to your old solution, this is the new molarity. Okay. The next ones there you're going to see, we don't use the next couple formulas as much. We use molarity all the time. We use dilutions. As a nurse, you'll be doing dilutions in your head 100 times a day. I promise you. That's why those two formulas, the M1V1, M2V2, and molarity, those are the two big bananas. Okay, those are the ones there that you will never, that you'll always use until you retire. Okay, but there are a couple formulas there that I want to show you. Are they difficult? No. Molality. This is a different way. Sometimes chemicals are shipped to us there in the lab, and they are not molar solutions, they're molal. Okay, molality is just another way of showing concentration. And this one here is moles of solute divided by kg of agua, water. So, have a look here. What is the molality of a solution prepared by dissolving a 10 moles of sugar into 500 milliliters of water? You do know that one milliliter of water is equal to 1 gram. That's a standard. So when you see, maybe I could give it to you 500 milliliters, well, you would have to convert this into 0.50 kilograms, and you just plug in and play. This is another triangle formula. There's some molality practice. And please note that whenever you see a small m, that is molality. Let's go back here. Whenever you see a big M, that's molarity. Write that somewhere, because you'll see that. And if you see a big M, I'm looking for molarity. Small m, molality. And again here, I've given you grams, 25 grams of water. There's a couple things there that you'll have to do. Grams, you got to change it to moles, okay? And for molality, it has to be kg of water. So you've got to be able to change 25 grams into kilograms. And if you have trouble with that, I can help you. Okay, shoot me an email. Being able to convert, you'll be doing it blindly by the end of this semester. Okay, and just a matter of plugging and playing. And the molality of this solution is 3.37. That's it. Plug and play. Yep. What do we got here now? Yeah. Osmosis. Very, very important there when you guys are going to get into blood. Maybe I have a great slide on blood. So maybe if you guys need it, ask me. I'll send it out to you. Osmosis is the diffusion of water. So you have, let's say you have a fish tank and you put a membrane of some type, something that will allow water to go through. And if there is an imbalance, for some reason, somehow there's not enough water over here as far as over here. Let's say I dump all the salt onto the one side. So the concentration of salt is very high. Water will move from a high concentration to a low concentration. Okay, so what will happen is water will move across a membrane, and you can do experiments there with red blood cells. You can blow them up. You know, when you can force water to go into them, they'll shrivel up if water is forced to come out of them. So the movement of water is osmosis only. So there are 3 words there that I want you to know. You'll have to know these there for week 4 blood anyway for your bio. Okay, isotonic, hypertonic, and hypo. Hyper means high, hypo means low. Okay, so isotonic, this is where the same concentration of dissolved particles. Okay, and hypertonic, there's a higher concentration of dissolved particles. Hypotonic is a lower concentration of dissolved particles. And you'll see there the effects of different concentrations of red blood cells. Isotonic, everything's cool in the gang. Hypertonic. What do you think's going on here? Okay. Have a look at hypotonic. All right. Have a look what's going on here. I'm not going to go too heavy into this because you guys, honestly, I'm going to give you guys a smackdown with chemistry. I'm not going to do it with bio. I'll let your bio teacher give you a smackdown for that. But have a look at those ones there. Okay. I'm not going to go too crazy into those. There might be a question. Okay. Just as long as you know hyper, hypo. Okay. Now this is I took this and put it on the formula sheet. These guys here, we don't use them as much but I might give you a question or two. There's a couple questions on the quiz. I think there's one there from molality. I'm pretty sure there's a mass volume percent. All these are just triangle formulas. That's all they are. So you see mass percent. How much solute is in the whole solution? And you get a percentage. Whenever you see a percent, you're going to solve the triangle and then you're going to multiply it by 100. I haven't dealt there with parts per million. It's I might next year. I haven't there this year. It's here. It's a simple formula. It's not too bad. Here we've got mass volume percent and volume percent. I'll show you all these. There's one slide each. And if I'm asking you for mass percent, I'm going to give you some information. You go and get your formula there for mass percent. You plug them in. Boom, get your answer. Next question. So here's mass percent. Calculate the mass percent of sodium chloride in a solution prepared by dissolving 50 grams sodium chloride in 150 grams of water. Well, there's my known. Okay. Now, you would go and find your formula there for mass percent, which is right here. So where is mass percent? So it's the mass of the solute divided by the mass of the solution. Now be careful. Sorry, I'm just going to zoom back out here. So what I've got, 50 grams of solute and 50 grams of solvent. The formula is the mass of the solute, so it's 50 grams on top. But the mass of your solution is 50 plus 150, so it's 200. That's the trick. Don't forget that one. Put a star beside that one because it's an easy mistake. Students all the time put 150 down here. You got to reincorporate the mass of the solute and put it down here because it's the mass of the solution. You divide it out, multiply by 100. There you go, 25%. Okay. Mass percent. Same kind of thing. What is the mass of sodium carbonate needed to make 350 grams of a 12.3% aqueous solution? Well, what do I give you? 12.3% is the mass percent. And I've given you 350 grams is the mass of the solution. Solute and solvent. Well, you're going to be working backwards now. I gave you the percentage. Please, you've got to change this back into 0.123 as a decimal. 10% is equal to 0.1. 20% is equal to 0.2. Percent and decimal are the same thing. If you need help with converting decimals and percent, let me know. And you just plug and play your numbers here. Okay. And away we go. Again, it's just a matter of plugging and playing. Try these out. Honestly, if you did 5 of these, you're doing too much. You know, do 1 or 2 of these questions there in the review and you're good because they become really boring after. And then you'll end up hating me. And I don't want you to hate me. Mass volume. Again, find your formula, plug in. That's all it is. There is, here's mass volume. Okay, again, another situation. Try it out. Okay. What do we got here? There's another one here called volume percent. And you see, I'll clearly state, because on a quiz or a test, you never know what question's coming next. It's a bag of mashed potatoes. You don't know what's coming on. You might be going from week 1 to week 5 to week 3 to week 4. There's no logic to it because that's the whole point of a test, right? And I'll always clearly state what I'm looking for. What volume of soda that is 6% by volume? Okay. There's only a couple of formulas that have percent. So 6% by volume, there you go. Fine, you got your formula. Pull out what you know, plug in what you know, get your answer, and away you go. Okay. I apologize if I'm going over this quickly. These formulas here aren't too bad. Here's another volume percent here. Plug and play, and away you go. So other than that, I think we're pretty good. The quiz 1 will open there this afternoon. and you'll see there the style. It's not going to be on the computer per se. You will have to put bubbles on, but I'm hoping there, the way that I've organized it there, you should be able to print off the quiz and doodle around with it there all week and practice it here and there or wherever. And then after you've looked at this lecture and practiced some of the questions, you should be you can answer the quiz today if you want. But my recommendation is, since it's on last week's class and this week's, which we're just doing now, take some time, review it. You have a week to upload it, so I think that everything should be good. Do you guys have any questions? Boy, where are my kids, man? What's going on here? They're usually hounding me. I don't know. But
hey, I have a question, Ian.
Perfect. Who am I speaking to?
You're speaking to Hunter.
All right, Hunter. How's it going? You good?
Here, I'll even put on my camera so you can see me.
Superstar. What's going on?
In a solution where, like, let's say chemical A is 40%, chemical B is 40%, and chemical C is 20%, are then chemical A and B both considered the solvent? Because obviously chemical C would be considered the solute. Is A and B, if they're at equal concentrations, are they both considered the solvent?
Now, you're saying, it's good. I like this. Now, you're saying chemical B, you put in, oh, go ahead.
No, go ahead.
If you have two, it's a good question, like which one is the solvent, which one's the solute, right? I'm not going to fry you guys too bad. And but in theory, yeah, if you have 40%, let's go back to air. Let's say you had nitrogen was 40% and oxygen was 40%. Well, in this case here, you'd have two solvents, right? And
okay.
But for you guys here, all intents and purposes, y'all gonna have one solvent, and we'll keep it easy. And because where you guys are going, like I am very job specific. I am as the course goes on, I will incorporate more and more health stuff there for you nurses, you paramedics, you firefighters, you vet techs, and that's where you guys are going. Did I miss any? Am I missing any? That the four that's coming off the top of my head? Is there anyone else who wants to be in something other than those four? Because tell me and I will include ideas from your job aspect into my lecture. So, oh, there's my beagle. But no, Hunter, that's a good question. Hopefully I answered it. Talk to me.
Yeah, I guess you just won't give us questions where that comes up.
I'm not looking...
And really, it's just a technical thing more than anything.
Sure. And that's basically the only difference between a solute and a solvent is which one more you got of. That's it.
As well as in the chat, I saw people were saying that massage therapy is also another big one that people are doing are going to go into eventually.
Oh, yeah. They're coming out with... that homeopathy is really starting to take charge, and like we all know, and we've known this there for a long time, that there is a huge connect between the mind and the body, and just like the Matrix, man, you know, there is no body if there is no mind, and health and wellness is total. And just to let you guys know, that if you guys will be feeling stress. Maybe you guys are all kind of chillax now, but maybe week 4, week 5, week 6, you're going to start to feel stress. And it's perfectly normal. There are two kinds of stress. One is good, one is bad. One is acute stress, which is short term. You got exams, you got assignment due, and you're up till 2 o'clock in the morning. That's good for you. It's the chronic stress, that the stress there of maybe somebody in your family who's been ill for a very long time. This is the kind of stress that it will take you down. So just be careful with stress. And all right, so I got massage therapy. So that's 5. Very good. Anything else? What do you got? Anybody? Oh, come on. You guys are all good? All
I
right.
have a couple of questions about last week.
All right. I like it. Who am I speaking to?
Chantal.
All right. How's it going? Good?
Good, how are you?
I'm all right. Now, where? Can I pull something up from last week, or where are we? What questions were you looking at?
I'm looking at the ones that are how many moles of hydrogen are needed to completely react with 2 moles of nitrogen.
All right. Where is that?
That's in the review.
The review week 1?
Yeah.
All right. Let's have a look. And quelle question, madame?
That's a good question. It just says solve each problem, and then it starts over 1, 2, 3, 4, and 5.
Yeah. So which one was that? Where was it?
It's under the balancing ones.
Okay. All right. So in here? Oh, no, below here. So we want...
There.
How many moles of hydrogen are needed? Okay. So this one here, and again, like this is titled mole. So you can go, this is the easiest of them all. All right?
I remember you saying that, and I couldn't place...
That's all right. Hey, this is all, it's just practice. Once it clicks, you got it, right? So, and you look at this one here, but you're not going to know that on a test because I'm going to give you gram, mole, gram, molecule, you know, and so you're going into this blind. So you're reading this. How many moles of hydrogen are needed to completely react with 2 moles of nitrogen? What's the very first thing you do, Chantel?
That's where I'm lost, I think.
Okay, good. Because if you're lost, that means that there's others that are lost as well, and that makes me happy. Or what's the movie there? Sad Happy? Sorry, I watch a lot of kids' movies. I have to. First thing you do is you make that molar ratio. That is everything. So right above, and you'll see on my quiz there when I open it up, and you guys can print it off. My equation is over here. So the words will be here, and the equation will be right here. So you guys can do all of your work right there. Your molar ratio is 1, 3, 2. You got that there, Chantel?
I think so.
All right. So you've got 1, 3, 2. That is written in stone. You cannot change it. In order for this reaction to happen, 1 mole of nitrogen must react with 3 moles of hydrogen to produce 2 moles of ammonia. That's it. But in this case, experimentally, I have given you 2 moles of nitrogen. So on top, you've got 1, 3, and 2. I've given you 2 moles. So you write a 2 under here. And I want to know how many moles of hydrogen. So you'd write an X under here. I don't know if you can kind of see what I'm doing with the cursor or not. But and from this information here, you would do a cross. And you would you'd have a 1, 3, 2, and an X. You crisscross and you solve for X. And I'm assuming that that would be, well, 1 mole makes 3 moles, 2 moles. I think the answer is 6. How's that going, Shen? Talk to me.
Yeah, that's what it says in the answer sheet. So that makes sense. I was thinking there was a cross there somewhere, but I couldn't figure out where.
Well, and even if you just look at the molar ratio, 1 mole of nitrogen, how many moles of hydrogen do I need? 3. So it's 1 to 3. So what if I had 2 moles of nitrogen? How many moles of hydrogen would I need? Double it. If I double this, because it was 1, now I have 2. If I double this, now I have 6. So that molar ratio is so important. Because when you get that, that is your go-to. That's all the information there that you need. And then I'm going to give you 2 moles of this. And I'm going to ask you how many moles of this do I need or can I produce based on that ratio. So talk to me.
And it's the same concept for the one underneath with the decomposition?
Oh yeah, it's all the same banana. What's my molar ratio for number 2?
So on top you would put the 2, 2, and 3, right?
Bingo. That's everything. Once you got that, the rest of it kind of falls into place with a bit of practice. And what information did I give you? How many moles of oxygen are produced by the decomposition of 6 moles of potassium chlorate? So I would write a 6 moles under potassium chlorate. And what am I looking for? How many moles of oxygen? X moles under here. And then you just do a cross from here, that little box there, and solve for X.
Okay, I think I figured that out now. I think I get it.
All right, now follow up with me in a day or so, because the quiz is, there are some of these mole questions on there. So there's gram mole, there's a couple of limiting, and I think there's one nasty one. But the rest of them there are all pretty clean. So have a look at those. Chantel, that's awesome. Great question. Any more?
The ones underneath
Y'all.
in the next square, are they going to be the same process, but they're grams instead?
You mean, can you see on the screen, is it this one here?
Yeah.
Oh, yeah. These ones here, you can, these ones here are exactly the same process. Your molar ratio for this one here is what? 2, 2, 3, right?
Yeah.
Molar ratio is in moles. That's how we do things in chemistry mathematically. Moles. If I give you grams, you can't do anything. You've got to change it to moles first.
So you're saying take the 25 grams and turn that into moles.
And then plug it in, do a box, there you go.
And then turn it back to get...
Yeah, because this one here is asking for how many grams. So after you do a box there, it's going to kick out moles. You've got to flip it using the triangle there and flip it back into grams.
So you would take your... hold on.
It's all good.
So if you have grams, you're looking for moles. You would take your grams and divide it by the molar mass to get your moles, then do it the way we just did, and then take that and times it by the molar mass?
Yeah, you'd use your formulas. The triangles there from week 1, you will carry those all the time. Because
they have been very helpful.
Well, I'm glad. That makes me happy. I don't know if you guys, if your previous teacher there from last semester used the triangles, but I find, you know what I mean, they're you don't have to memorize them. They're on a page. Put your thumb on it. Wait, you know what I mean? Just the easiest way to get to point B. That's just all I'm looking for. So, no, that's good. What else you got, Chantel?
I think that's it at the moment.
All right. It's all good. Is there anyone else? Talk to me. If you guys got nothing, I got nothing. I don't even know what time it is, but I'm going to turn off the video. I'm going to turn off the video here. Now, give me 2 seconds and